This video is about partial fractions with repeated, irreducible, also known as prime, quadratic factors. If you've been following this series of videos, you'll know we're doing several different cases of this partial fractions process, but all the cases have some general steps, and of course this case does as well. So we'll consider the numerator degrees, the degree of the numerator and denominator, and compare them. Secondly, we'll factor the denominator if possible. Thirdly, we'll set up a decomposed rational equation. Fourthly, we'll clear the fractions in that equation. And then fifthly, we'll find the numerators of the decomposed terms either by substituting convenient values, which we've been seeing a lot of so far, or if that doesn't work, secondly, by creating a system of equations to solve for the new numerators. Let's consider this fourth case now, where the denominator has repeated, irreducible, known as prime, quadratic factors. Now, there's some overlap with some of these cases. For example, you'll notice that we've already done a repeated case. We did a repeated linear factor case. So the repeating that happened in that case will actually mimic the same thing in this case. We've also encountered a prime quadratic factor in the denominator, and so what we used for that numerator will also show up in this case. So we're now kind of just combining some other cases that we already know in this fourth case. Now, the decomposed numerators are degree 1 linear. That's because of the quadratic nature of those denominator factors. But then we see this repeating thing happening again here, where repeated quadratic factors of denominators must occur in incrementing powers per decomposed denominator up through the original power of the quadratic factor. So we saw that, it's a lot of words, I know, we saw that exact thing happening in the repeated linear factors, so we're going to do the same kind of thing for these, and of course we'll note that multiple cases can occur at the same time. Let's try an example where we want to find the partial fraction decomposition for the following rational expression. The numerator is 3x cubed minus 6x squared plus 7x minus 2. The denominator is a trinomial in parentheses. The trinomial is x squared minus 2x plus 2, and then that whole trinomial is squared outside those parentheses. So if we consider our steps, of course, we'll compare the degrees of the numerator and denominator. Don't forget that when this denominator trinomial is squared, you really would be adding up those powers so that the denominator is degree 4, the numerator is degree 3, which means we're already set up without the need for long division. We'll skip that step and go right on to the step where we try to factor the denominator we have. But notice, it's already in somewhat of a factored form. There's a trinomial that's squared. So if we look at that trinomial, if we can factor it further, we should. But a little effort in doing that would reveal that it's actually not factorable further. X squared minus 2x plus 2 does not factor, which means that is our irreducible or prime quadratic factor. But because it's all squared, that means it's repeated. So now we're going to put all of this together, and let's start writing our rational equation where we simply copy the numerator first. So 3x cubed minus 6x squared plus 7x minus 2. That's just the original numerator. And then the denominator we're going to copy down as it is, right? It's not factorable, so we'll just repeat it one more time. So x squared minus 2x plus 2 in parentheses all squared. Now we're trying to create our decomposed rational equation, and we're going to combine a couple things we already know. All right, first of all, when you have repeated factors in a denominator, remember you have to increment from the first of them all the way up to as many as you have, which in this case is 2. That means we're going to have 2 fractions for our decomposed rational equation on the other side here, and the first of them will be a single power of that quadratic denominator, so just an x squared minus 2x plus 2. And then the numerator for a quadratic denominator, remember, is degree 1 linear, so we're going to have to put an ax plus b in that numerator. Okay, and now our second denominator is going to be, remember, we have to increment up to our highest power of that repeated factor. So that means the second denominator is going to be an x squared minus 2x plus 2, but that's all squared now. To handle, we have to get up to that squared power, incrementing our way up. Okay, and then that numerator will be also degree 1 linear, but we can't reuse any of the letters we've already picked, so why don't we say cx plus d. Okay, our rational equation is set up. The next step would be to clear the fractions. Of course, we're multiplying by our original factored, it's actually prime, we can't factor, but our original denominator is going to get multiplied all the way through, which would of course take it out in that first fraction on the left side, leaving us just with 3x cubed minus 6x squared plus 7x minus 2 on the left side. On the right side, first we have an ax plus b in the numerator. We have to keep that bundled together. But then when I multiply by this quadratic denominator squared, it will cancel with that denominator, but still leave one of them behind. So we'd have an x squared minus 2x plus 2 in parentheses after that ax plus b. Okay, moving on to the last term, of course, the entire denominator would cancel in this fraction clearing process, leaving us only with a cx plus d. Okay, at this step, as you may recall, it's our turn to try to find all these new numerator variables, a, b, c, and d. This time we have 4 to find. Now, as you'll recall, our methods for finding those would ideally include the step where we can pick some value for x, some convenient value for x, that when plugged in would cause all but one of our variables a, b, c, and d to disappear in this previous step so that we can find it. And then usually it's kind of like a domino effect. Once you start finding one or two of them, usually you can get the rest. But in this case, there's actually no value of x that we could pick that when plugged in would eliminate all but one of our a, b, c, and d values. I mean, just think about it, or maybe even just try it. If you pick x as 0, the a would be gone, the b would not, the c would be gone, and the d would not, right? But if you have an equation with two variables, you can't solve for either one of them. So 0 doesn't work. I mean, you can go through the list. Nothing will work where when plugged in, we'll eliminate all but one of our variables to find. So that makes us fairly unhappy, but it doesn't mean we can't do anything here. So the other method listed in our notes is going to be to try to set up a system of equations to handle this. Now, it's a little bit of work to get there, so let's go ahead and clear some space. The first step in setting up the system is to completely expand the right side of our equation. So I'm going to rewrite this equation again, just copying down the left side as 3x cubed minus 6x squared plus 7x minus 2. But now on the right side, I'm going to expand those binomial times trinomial factors we have there immediately to the right, which means I have to distribute the ax all the way through all the terms and then the b, right? It's kind of a lot of work, but we've seen this algebra a lot before. So let's do this. We'll end up with ax cubed in the first term minus 2ax squared in the second term, and then plus 2ax in the third. Now we go back through and distribute the b. That will turn out to be plus bx squared minus 2bx plus 2b. Now, we can't forget also we have this plus cx plus d floating up here. I just kind of ran out of room horizontally to put them in, but that's where they are. Once we expand everything, that's our main goal here, and notice it's kind of separating all of the terms on the right side. It looks like a complete mess. I agree, it is. But let's try to collect those terms in ways that would organize the like terms of them. For example, let's rewrite this again. So on the left side, we still have 3x cubed minus 6x squared plus 7x minus 2. But now moving on to the right side, notice there's only one x cubed term, so I'm going to put that first, ax cubed. But then for the squared terms, note the x squared terms, notice there are a couple. There's this x squared term there and there. I think those are the only two. So here's what we're going to do. We're actually going to factor out the x squared from those like terms. Okay, so hold on here for a second. I'm going to take whatever was in front of those x squareds, which happens to be a negative 2a and a positive b. And I'm going to write that in parentheses. I'm even going to reorder it so it looks better. So b minus 2a, that's just the coefficients of those x squared terms. But then I'm going to write the x squared after them. So it's factored out, but normally when we factor out stuff, we write it in front of the parentheses. I'm purposely going to write it at the end just so it looks clearer at the next step, okay? But we're going to do that for the like terms of x squared, and actually we're going to do the exact same thing for the like terms of the x's. Notice there's a 2ax, and there's a negative 2bx, and there's a plus cx. That means if I factor out all the x's from those terms, I'm going to put all their coefficients collected in a set of parentheses like we did for the x squared term coefficients. Those would turn out to be 2a minus 2b and then plus c. So again, those are all the coefficients of the x terms. There's the 2a, there's the minus 2b, and there's the plus c. They're all showing up here. And then like we did previously, I'm going to put the x after them, which again looks a little weird, but that's how we're going to factor those out. Now, there are a couple terms left that we have not addressed. Can you find them? It'd be the plus 2b and the plus d. So we can't ignore them. We have to put them in. I barely have room. I'll try to squeeze them in here at the end. So plus 2b and then plus d. Okay, now let's just pause for a second and try to figure out what in the world we're doing. If you go back and look at where we came from, we're trying to find the partial fractions for this original expression, rational expression. And in doing so, after going through the steps and using this case 4 with repeated quadratic factors, we got to the step where normally we would try to pick convenient values of x and plug them in to solve for a, b, c, and d here, but it didn't work. There was no convenient value of x that worked. So here's our second effort, which is to expand everything completely and then factor the right side so that all the like terms are factored out, meaning I have an x cubed, then an x squared, then an x, and then my constant terms. And I've factored out what would be their coefficients from that previous step, which are now in front. The a, the b minus 2a, 2a minus 2b plus c. Those are all the coefficients. Now, the next step is actually a lot easier. We've done all the hard work. The next part is fun as long as we've done everything correctly. All we're going to do is now compare the left and right side of our equation and find things that are lined up. So notice we only have one x cubed term and its coefficient was the 3. Well, notice on the right side we only have one x cubed term and its coefficient was the a. So simply by matching those up, that immediately tells us that a has to be 3. Well, there, we found a, just like that. Moving on, notice for the x squared terms, if we compare the left side, the coefficient was a negative 6. On the right side, the coefficient is b minus 2a. Well, if those are the only two x squared terms, one on the left and one on the right, then their coefficients must be equal. So that immediately tells us that b minus 2a must equal negative 6. Okay, but hold on. If a is 3, which we already know, then that tells us that b minus 2 times 3 equals negative 6. And actually, we could solve that for b easily. This just tells us that b would be 0. Okay, you may be able to tell where we're going next. We can compare the x terms. Notice on the left side we have a plus 7x. On the right side we have this 2a minus 2b plus c as the coefficient of x. Well, that simply must tell us then that 2a minus 2b plus c, that's that coefficient on the right side, must equal the coefficient on the left side, which was just 7. Okay, but again, we already know a and b, so if we put those in place, plugging in the values we already know for a and b in this new equation would allow us to solve for c. In fact, it would tell us that c must be 1. All right, so now we've found A, B, and C, but notice we're not quite done. We do have this variable D at the end. So let's take one more step in this direction where we're still comparing the left and right sides. Notice on the left side, we have not dealt with this -2 constant term yet. So that's next. That constant term, which does not have an x with it, of course, would have to equal the constant terms on the right side, which don't have an x, which in our case is 2b plus d. So that would tell us that 2b plus d must equal -2, comparing those left and right sides. But we already know b is 0, which means d must be -2. So there we have it. So this is the long way, but sometimes it's the only way when you cannot pick convenient values of x to solve for a, b, c, or d. And this does work. We now have them. We can go ahead and write our answer in final form. Our first term in our decomposed form was the single power of that prime quadratic factor, so just x squared minus 2x plus 2. And you'll recall its numerator was ax plus b. Well, a is 3, so really that means 3x, and then b is 0, so we really don't even need to put the plus 0 there. So that's our first term, and then our next term, as you'll recall, that was the squared version of our prime quadratic factor, so x squared minus 2x plus 2, that was all squared, and that numerator was the cx plus d. Okay, but we found all these values, so plugging them in, c is 1, that just means x, and then d is -2, so x minus 2. So this now is the decomposed version using partial fractions of our original rational expression.